Well, we've got several participants. We have Adam. Hello, Adam. And Levi. And we're just waiting on the others. We're a little early, but that's all right. I gave you some problems to work on. We can do those. Well, we don't have very many right yet, but we'll be patient. The topic for today, we're going to study AC circuits. Hey, there's Kristen. Kristen just logged in. Good deal. Well, she's connecting. There you go. Kristen, hello.
You, Professor Griffin.
Yeah. Well, okay. We have about 7 minutes before class. If anybody has a question, go ahead. Well, and you were supposed to do a couple of problems to work on. Let me put those up here. We'll do those. You were supposed to do 1457. Let's talk about that. We're going to talk about 1457. Let me see what that is. I was just thinking about this summer. I was supposed to teach a course this summer. How are they going to get their books? I think I'm teaching thermo this summer. If the bookstore is closed, how are they going to get a book? You guys have that figured out yet? I don't. Maybe through Amazon? I don't know. Okay, we're looking at 1457. The current in the RL circuit reaches half its maximum value, blah, blah, blah. Let me draw it here. Okay, now there's our circuit. What do we know about it? Not a whole lot. We do know this is 250 millihenries. That's the inductance. But we don't know the resistor. And we don't know the battery either. All we know is that there's an equation that we know. It goes like this. I'll use little letters here. There's the equation. Now we don't know the maximum current, but they did tell us that you reach half of the maximum value in 1.75 milliseconds. So let me write that in. You reach 1/2 of the maximum value in 1.75 milliseconds. I heard something. Hey, we have a lot more students. Look at all these. Tyler, Trevor, Nathan, Mark, Levi, Kristen, Jeff. Jeff is here. Yay. Adam, Zach, Muhammad. We got a good group. And we're going over 1457. I gave it to you to work on, but not to turn in. I'm starting to total up everybody's homework to get a total. Wouldn't that be nice for you to know what your homework total is? Well, I'm working on it. Okay, now back to this. We're going to do a little algebra here. Can I just lock that off, algebra students? Yeah, I can do that. And then what I'm going to do is I'm going to subtract that 1, and I'm going to get, here's what I get now. I get a negative 0.5 equals a negative blah, blah, blah. Hey, Adam, how do you say blah, blah, blah? Oh, that's wonderful, Adam. Okay, now, hey, look, an equation with only one unknown. I can do that. Lop off the negatives. We don't need those stinking negatives. Get rid of them. Just get rid of them. We don't need them. Okay, well, we're going to take and do a little math here. We're going to take the natural log of both sides. That's certainly legal. The natural log of 0.5 would equal the natural log of this here. You're supposed to put units in brackets. I forget sometimes. That doesn't say misses or miss. That's milliseconds, okay? Yeah. Now, when you do that, here's what I get. I get a negative 0.69 blah, blah, blah equals, you know, when you take the natural log of e to the something, guess what you get? You just get the something. It's a math thing. If you don't understand that, I would say go talk to your math teacher, but you can't do that unless you're online. So you guys can do that. You've studied math, I have no doubt. All right, now I'm going to solve for tau. Here we go. Tau is going to be wonder if this is right. I'm getting a very small number, but I can't help it. I'm getting a 2.52 something. It's really milliseconds, isn't it?
Yeah, that's what I got.
Yay! I bet we did that right. Now let's see what they wanted us to do. Let me read this again here. Determine the time constant of the circuit. Well, we just did that. That is the time constant. Ta-da, that's it. It's a Greek letter tau, and it's the time constant, and it's in seconds. Yay, we did that. Now, what else are we supposed to do? The resistance of the circuit. Well, look here. I need a little room here. Here's some room right in here. Tau is equal to L over R. Remember, L comes before R in the alphabet, so it's L over R. Okay, now if you know tau and you know L, well, you can solve for R. I'm going to do that now. I know tau, it's right here. And divide that into L, and here we go. L is a 250 e to the minus 3. Boy, Jove, I'm getting 99 ohms. Yay, that's it, 99 ohms. And look up the answers in the back, and I think we got those right. I think,
That's what I got too.
yeah, those are right. You can double check it. So we did that, that's good. And if you got those, I'm proud of you. Now let's do the other one, and then we'll give you a virtual quiz, okay? It's just a pretend virtual quiz. That'll be fun. See, I like to give quizzes every day, but with the regular class, I give you a quiz and I grade it every day. But we can't do that, can we? Okay, now this is problem 79. If you're happy, I'll wait. If you have any questions on 1479, I'm waiting.
Quick question, because I wasn't here when you guys started. Why was it 0.5? Where did you get the 0.5 from?
Oh, thank you for asking. They said that this is the equation.
Mm-hmm.
I don't know if I derived that for you or just told you about it last time, but that's the equation. And if the current is half of the maximum, put it in there. It's 1/2 of,
Okay.
and look, you can just lop off that from algebra.
Mm-hmm.
So you get 0.5 equals this. There, that's where I jumped up to here.
Yep.
You okay? You okay now?
Yep, that makes sense. Yep.
Yay. Okay, anybody else before I erase this one and we'll tackle the next one? Okay, we'll say goodbye to that one. Now, a lot of you guys don't have a physical book like me. See, I've got a physical, I like that. But some of you guys just have an electronic book, don't you? What am I going to do
Yep,
this?
that's what I use.
Yeah, well, that's okay if you're comfortable with that. Okay, now, right now we're doing, I think I asked you to do 1579. Let's do that.
14.
Hey, our first thank you point of the day goes right there. You're absolutely right. We're going to be in 15 today, but we're not there yet. Okay, now let me draw this, and we'll figure it out. .03 ohms, 1 Henry, and 5 ohms and 12 volts. Okay, let me read this now. This is problem 1479 in my book. I'm on page 667, but you might have a different page number on your electronic book. I don't know. It says the switch S is closed at time 0. Determine the initial current through the battery. Okay, let's do that. But we're going to throw this switch. Here we go. Clang. We just close that switch. And what's going to happen is the pluses in coming out of this battery are going to head that away. They want to go around this circuit. We want to have some current, but there's a problem. Inductors are like flywheels. I was telling you about that. When you turn on my grinder, which is a flywheel in my garage, it doesn't just immediately go to 800 RPM. It starts off with 0 RPM, and then it goes to maybe 50 or 100, 200, 300, 500, 800. But it doesn't do it immediately. And so when you first throw that switch, the current through here is 0. 0 amps is what you had before. And immediately after you throw the switch, 0 amps is what you have now. It's going to build up. And there'll be a current, all right. And the same here, there was 0 amps in this coil here, in this inductor here. And so there'll be 0 amps immediately after you throw the switch. Well, there's no current anyplace. You know what? There's no current here, no current anyplace. Okay, well, we could even get the voltages. The voltage here will be 0 volts. And the voltage here will be 0 volts. Because there's no current. There's no current going through here or here. And so you have 0 volts. But now, wait a minute, Auga, you have 0 volts here, but you don't have 0 volts here. You have plus minus 12 volts. Because Lentz's law says that when you're trying to increase the current in an inductor, it kind of acts like a battery, and it's trying to shove current back the opposite direction, if that makes sense to anybody. But now you don't have any voltage across this inductor because it's in parallel with this resistor, and it's got 0 volts. So whatever the voltage is here is the same here because they're in parallel. Remember, in parallel, the voltages are the same. So Kirchhoff's voltage law goes this way. You go up 12, down, you don't change any, and then you go down 12, and then you don't change any, and well, you're back to 0. Up 12, down 12, you're okay. You could go around the outside. You could go up 12, down 12, there's no change in voltage, and you're back to 0. So that's what happens when you immediately throw the switch. Read the problem. The initial current, we did that. It's 0. Then part B, they want to know the steady state current through the battery. What they mean is, after a while, after several time constants, usually 3 time constants would do the trick. So I don't know how long you need to wait. What would be the time constants involved here? Well, they're pretty small. Just give it a day or two, okay? Or a couple of minutes would work. But see, after a while, the current will build up and it will be steady. And once it reaches a steady constant value, the voltage on the inductor is given by this here. And if this current is a constant, which it will be if you wait a few minutes, it'll even out. What is the derivative of a constant? Well, it's zero.
0.
Yeah. So you don't have any voltage. Remember, it was 12 volts when you first threw that switch, but after a few minutes, it goes down to 0. You don't have any volts there at all. And the same here. You don't have any volts on this guy here. Well, now wait a minute. I'm getting mixed up now. Just a second. It has to have the same volts as this. But let me think about this. You've got 5 ohms here, 3 ohms there. I think that your entire current will go through this. It will go through here. There won't be any current going through here. How do I explain that? It acts like a short.
It becomes the easiest path for the electrons to flow through.
Yeah, and all the current. You could replace all this with just a short, because when you get to the steady current after a few moments, the voltage across here will be 0 because the current will be a constant, whatever it is. And so if the voltage is 0, guess what the current is in here? Well, it'd be 0. E equals IR, guys. And a resistance.
But doesn't the voltage there need to equal the voltage on that? I'm blanking on the name of it, but the thing to the right of it.
The inductor has a voltage of 0. That's what he was saying.
Oh, the inductor has a voltage of 0 as well.
I think the voltage has an inductor of 0, but the current isn't 0. You got current in there. It's acting like a short. You have 0 volts on the inductor, 0 volts on the resistor, and all the currents going through here. And I tell you how much current that'll be. It'll be 12 volts divided by 5 ohms, which is 2.4 amps. After you let this thing settle out, after a little bit, a couple of minutes or so, you're going to get 2.4. Here, let's erase the other stuff and we'll figure it out here. We'll get it figured out. We're talking about after a couple of minutes, after several time constants, you'll have 2.4 amps here. And our volts will be 12 volts here. Negative plus, plus minus. You'll have 0 volts here. You'll have 2.4 amps. The 2.4 amps will come through here, but you'll have 0 volts on the inductor. And then you'll have 0 amps coming through here and 0 volts. There's no voltage, so there's no current. 0 volts, but you'll have 2.4 amps steady coming through here. No voltage because the derivative of a constant is 0. So that's what you have after, how did they put it? Steady state current through the battery. The steady state current through the battery should be 2.4 amps.
Okay, is this because the resistance of, and I keep on blanking on its name, but the inductor, the resistance of the inductor just goes down to 0 basically?
Yeah, they don't call it resistance. They have a fancy name, and I'm going to talk about it. It's today's topic. It's called reactance. It does oppose current, kind of like my my grinder opposes. It opposes the turning because it has inertia. Because see, what you're doing when you run current through here, you're increasing energy. And it takes time to increase energy. You can't just go from 0 energy to a high level of energy instantly. It takes time. So it opposes that. If you're trying to change the energy real fast, it opposes it. Well, if you look up the answers, I bet that's what they say for the current. What is this? 1479. Let's look it up. Let's see here. 1479. It's a little bit tricky, wasn't it?
Mm-hmm.
1479. And I'll give you a pretend quiz here in a minute. Let's see, 1479. They said 0 amps to start with. Remember, I erased it, but when you first threw the switch, you had 0 amps. However, you did have voltage on the inductor. And then they said 2.4 amps after the thing reaches steady state. So we got the right answers, and I'm pretty happy about it. Any other good, or they don't even have to be good. Any other questions? I'm listening. Okay, well then let's have a virtual pretend quiz here. Here we go. I'll erase all this stuff. Let's see if you guys have listened to me and have really learned this stuff. And there's a thank you point. I forgot what it was for, but somebody was on the ball there. Oh yeah, it was somebody knew that we were in chapter 14. That's what it was. Okay, now here's our pretend quiz. We're going to have a virtual quiz now. We've got to get ready for our final. See, today is the 22nd. It's Wednesday. We have one more week after this of these wonderful lectures, and then I was thinking that Sunday night I will post your final. That would be the May
3rd.
3rd. And if we had the final due at midnight on Wednesday, that would give you plenty of time to work on it. It's 72 hours, I guess.
Mm-hmm.
Non-stop. You drink a lot of coffee and get my final done and turn it in to me. And see, I can start grading them on Thursday morning. That's the big plan. Okay, here comes your quiz, your virtual quiz. All right, we're going to take 12-volt battery. I hear a horn. I think it's my neighbor. They got one of those theft alert horn thingies. Those things are irritating. It quit. Okay, I just made these up for practice for you. And what we're going to do is we're going to throw that switch at time 0. When we start our stopwatch, we're going to throw the switch. And at let's do it this way. At 2 seconds, when the time is 2 seconds, I want you to find. Well, you could find the current. That'd be good. The voltage on the resistor would be good. Find the voltage on the inductor. There's your inductor. And the book uses U for energy. Find the energy stored in the inductor. And remember, the equation goes like this. Okay, now I'm going to shut up and let you guys work on that. And we'll check it here in a few minutes. And if you had one like that on your final, you'd do great. Okay, go to work. Well, I'll give you a little bit more time, maybe another minute. Some of you might need another minute. Okay. I think it's raining here. I'm going to look out the window and see. I'll give you a weather report. Yeah, there's a little bit of rain coming down out there, not much. Well, I gave you a little time to work on that. Let's go through that. Okay, need a little room here. There's lots of room up here. Let's use this up here. I'm gonna move that thank you point over here someplace. That'll give me even more room. Uh-oh, I heard that boom boom. I'm unplugging my charging for the computer.
I heard the same boom.
Yeah, did you really? Well, I unplugged the charger. I don't want anything bad to happen to my computer. Then we'll all be out of luck. So I'm just working on the battery now. Okay, now the first thing you got to do is you have to find the time constant is tall. There you go. And it's equal to L over R. And L is 16 henries. 16 henries. and R is 8 ohms. And if you remember, a Henry is an ohm times a second. And if you divide by 8 ohms, guess what you get? You'll get 2 seconds. So the time constant is 2 seconds. Yeah. All right, now we'll write the equation. And there's some room here. This might be good. If you want the current, it's going to be 12 divided by 8. See, after a while, when there's no more voltage here, the voltage goes to 0, remember, when the current is steady. Then all you have is 12 volts, 8 ohms, and you get 1.5 amps. And here's your equation that we know and love. And the time, we're going to do it at 2 seconds. So you have T, 2 over tau. There you go. Hey, well, tau is...
Got the resistance on the current equation.
Say that again, please.
Oh, I was actually ahead, and I was gonna just say you forgot the R on the current equation.
Where did I forget the R?
No, it's actually a next step, so it's okay. That's fine.
Everything's okay.
Yeah, everything's okay. That's fine.
No thank you point yet.
No.
Not yet.
No.
No thank you point yet. Okay. Well, you know what? This is 2 over 2. That's just a 1. I can do that. I can take e to the minus 1. Here goes. I'm going to find the current now. All right, e to the minus 1. And then you subtract it from 1 times 1.5. Okay, I'm getting 0.948. We'll round it off to 2 amps. We just got the current at 2 seconds. Now, we did that. Yay, check. We got that done. Now we're going to find the voltage on the resistor. Well, that's just going to be V equals IR. And you got the current. Now we're going to multiply by 8. And I'm getting voltage on the resistor is 7.585 volts. Okay, now we're going to get the voltage on the inductor. Well, you see that plus this has to add up to 12. Just subtract that from 12. Did you get 4.41, I don't know, 5 volts? We just got the voltage on the inductor. Okay. Now we're going to get the energy stored in the coil or the inductor. Here goes. Well, it's we know all of this stuff. We know L. It's 2 seconds. Yeah, there it is. No.
16.
It's 6. I didn't write it. I didn't write it. It's 16 seconds. And we know I. We just did I. So I'm going to do that. Here goes. 1/2 times 16 henries times 0.9482 squared. Well, I got an answer. I'm getting 7.193 joules. How about you guys?
Yep.
Yay! Good going. We did good on our virtual quiz. Anybody else comment or question before we tackle chapter 15 today? Okay, well that's fine. Let's move on here. I'm gonna say goodbye to all this stuff. We're gonna start in chapter 15. Chapter 15 is pretty important. It's AC circuits. And we've worked with some AC. We've had AC in the lab when we used to have labs. Remember those days?
Mm-hmm.
And I'm hoping they'll come back because I really think the labs are needed. Doing things by computer is fine, but I think the labs are important. Okay, AC, what we got here is we have a, we'll start with just a resistor. And this is their symbol for an AC voltage, and the voltage they picked was some maximum value. You could put maximum on there if you wanted to. And it's a sinusoidal voltage. For this omega is an angular velocity. Your book sometimes calls it an angular frequency, but I really prefer the term angular velocity because it's radians per second. See, the turbine, the generator at the power station rotates at 60 hertz, 60 turns per second. It's rotating, and that generator has a coil in it, and it produces electricity. It produces sinusoidal electricity that looks like this. It goes up to a maximum value, and then it comes down, and it's a sinusoid. You guys have all studied sinusoids. This is the voltage, and this is time. And you've got a sinusoidal, it varies sinusoidally, and this amount here is V max. And this amount here is negative V max.
How can you have a negative voltage?
That's how AC power works. It goes back and forth. It buzzes back and forth at 60 times
Right.
a second.
Yeah, the current sometimes is plus minus, and you run the current this way. And when the current is going this way, you all know that the voltage is plus minus. Well, it has to be plus minus because they're in parallel and they have to have the same voltage. But then what happens is the current goes the other way. And this becomes plus minus the other way. And this will be plus minus, and the current will be going the other way. The current goes back and forth 60 times a second. And it makes a hum.
Yeah, if you ever stand next to a transformer, you can really hear them hum.
You can hear the 60 cycle hum. Yeah, it's a distinctive, kind of a low hum.
At my work, we have our own transformer room, and it's like 15 kVA, and we keep it locked. When you go in there, your hair stands up.
Yeah, it could be scary. Well, that's the voltage. Now, what about the current? Well, we'll try to put that in a different color. Do they use a different color? Yeah, they use red. We'll try to use red. The thing about resistors, the voltage in a resistor is equal to the current times the resistance. They're in step. So if the voltage is 0, the current is 0, see? And it'll be maximum when the voltage is maximum, but it'll be the current. Well, I'll draw it for you. They do this in your book. Here's the current in the resistor. It's a sinusoid. There it is. Here, I'll make this darker so maybe you can see it. There you go. And see over here, that's your maximum current. You can plot it on the same graph. Do they do that? Yeah, they do that. Look on page, I'm on page 670. They have the same graph on page 670. And if you wanted to know what the maximum current was, well, it'll be the maximum voltage divided by the resistance. You can get that from that Ohm's law equation. And they're in step. They just follow one another. And then on page 673, they introduce the idea of voltage and current phasors. They have a phasor diagram. They have the voltage like this, and then they have the current. I'm drawing mine a little different than theirs. I think they changed colors on me here. They got their voltage in red, and they're confusing us here, and the current in blue. And over here, they have the voltage in blue and the current in red. Oh, well, we won't get too confused, I hope. But here's your voltage phasor. There's your Vmax. And see, it's spinning around in a circle. And this thing is called a voltage phasor. That's the name of it. And what a voltage phasor is, it's a rotating vector. This thing is rotating. Now, when it's right here, this right here is going to be your Vmax sine of this angle. See the Vmax sine of the angle? That's the angle. That angle in general is omega t. Depends on the time because it's changing all the time. But you could say it's theta if you wanted to. It's Vmax sine of theta. Now when it's up here, when your phasor is up here, this right here will be Vmax sine of theta, but see the theta is bigger because this thing's spinning. Now when it's over here, do you see this distance here? That'll be Vmax sine of theta, only the theta there goes all the way over to here. This thing goes around and around. If it's 60 cycle, it goes around and around 60 times a second. Now when it's down here, I don't want to run into my pretty diagram. Say it comes around and your phasor's over here. Here's your Vmax. It's spinning around, and this is your, you've studied trigonometry, you know that's the opposite side to your angle. I know the angle's really going all the way around, but you could use this angle here, only call it a negative angle. It gives you the same answer. And this distance here is Vmax sine of that angle. In general, it's omega t. Whatever the omega is the radians per second. You multiply by your seconds and you'll get your radians. They call those voltage phasors, and there's also current phasors. Now, the current phasor, since I did the current in red, I'm going to do the current phasor in red. Now, I made it smaller, but see, that all depends on the value of your resistor. But I'm going to put my current phasor right here. And there it is. That's Imax. That's your maximum current. And it spins around. It's in sync, I guess you could say. It just follows the voltage. When the voltage gets bigger, the current gets bigger. When the voltage gets negative, the current gets negative going the other way. And that's called your current phasor. Okay, great. Well, we studied resistors, and they tell you about that on page 672. Now let's study, what's next? Maybe, let's do capacitors next. There's a page here in your book that tells you about capacitors. See if I can find it here. I found it. This happens to be in my book on page 673, and we're going to talk about capacitors now. Okay. I need the space here to do capacitors. So we're going to scrap all this for just a moment, and we're going to look at the same thing, only this time it's going to be a capacitor. I didn't mean to erase that. You have a maximum voltage times the sine of some angle as it spins around. Now, when it's plus minus, well, this will have to be plus minus because it's in parallel, and you know voltages are equal in parallel. And see, currents coming in. The pluses are going this way. There's current coming in, and it's filling up this capacitor, and it's making this side plus. And then it's repelling the pluses here, and they're going to the negative. Then it switches, see, and then the current will go this way, and it will fill this side up with pluses. This will be negative, and the current will go the opposite way, back and forth. Okay, well, great. What do we know about capacitors? Well, the definition goes like this. And you have that memorized. You know that tells you what capacitors do. They're charge, it's the capacitance is the amount of charge per volt. And the units are farads. And what a farad is a coulomb per volt. That's what a farad is. And you knew that. Yeah. Okay. Well, so what? Well, look at this now. See if you can get to here with me. Q equals C times V. Yeah. This is really a definition, guys. That's the definition of capacitance. And so you can get from there to here, no problem. Good going. And why don't we write this as C times V max sine of omega t, because that's what little v is. If you have an AC circuit, that's what an AC circuit does. It's a sinusoidal voltage applied to your circuit. Now watch this. We're going to take the derivative of both sides. We're going to take the derivative of the charge with respect to time. Does anybody know what the derivative of charge with respect to time is? What is that?
Current?
It's current. We're looking at current now. And we're going to write the equation for current. Now, when you take the derivative of this, that's just a constant. That's C. C is a constant, whatever it is, 120 microfarads. It doesn't change. And V max, that's not going to change. The V max, that's when you plug in stuff into your wall socket, it's really a constant. Now, the voltage changes according to this equation, but the maximum Well, sometimes it's plus and sometimes it's minus. It's a constant number. And then what's the derivative of the sine? Well, they taught me in school it's the cosine. But now here's the tricky thing here. When you're taking derivatives with respect to time, you have to use the, what do they call that in calculus? They call it
It's like the chain rule.
chain
I think.
rule. Chain rule, good thinking. Chain rule. So you have to take the derivative of that with respect to time, which is omega. So you can stick an omega out here. I'll just stick it out here in the middle, maybe. But you have to take the derivative of that according to the chain rule. If somebody really is desperately lost on that, speak up and I'll explain it. Now they have something sort of like resistance for capacitors, but it's not called resistance, it's called reactance. And the definition of it is they have a symbol. It's XC. Now that'll be capacitive reactance. Capacitive reactance is, the symbol is XC. And what that is, it's kind of like resistance. You take your voltage and you divide by your current. You take your maximum voltage, you divide by your maximum current, and that is the definition of, that was supposed to be triple, I don't know if you can see that, but that's really a definition of what reactance is. Now, hidden right here is a little secret. That stuff right there is your Imax. So you could write this as Imax cosine of omega t. It's just a constant. Omega is a constant. It's 60 hertz for the United States. C is whatever capacitor value you have. And Vmax is also a constant in the United States. And now let's do this with me and let's see what we get. We get Vmax divided by omega C Vmax. You know what I get? I get 1 over omega C. We have just found the capacitance of, no, not capacitance. We've just found the reactance of a capacitor. And that's in your book, I'm sure. And there it is. I see it. It's on page 674 in my book. This comes out to be in ohms. Let me show you why it's ohms. Let's do that up here. This is called capacitive reactance. It's 1 over omega C. And I'm telling you that's in ohms. Capacitive reactance is in ohms. And now omega, you know what omega is? That's 1 over, well, it's radians per second. So it's 1 over seconds. Hope you can read that. Maybe you can.
Yeah, that's good.
Okay. And now capacitance is farads. Now somehow we have to show you that that's going to give you ohms over here. Well, I'm going to play with it for a minute and let's see what happens. You know what a farad is? That's a coulomb per volt. So we have a coulomb per volt. Don't forget to divide by seconds.
Wait, a farad is a coulomb per volt?
I wrote it wrong. It's a Coulomb per volt. Well, here, let me write it this way. It's a Coulomb per volt. Now you have a second there to worry about, and then you have volt.
Yep.
And now this time I have it right, but I'm going to give you a thank you point because I did make a mistake there. I had the wrong thing. Now somehow we have to show you that that's, well, look at it this way. That volt goes in the numerator, and then you have a Coulomb per second in the denominator. You know what a Coulomb per second is?
Isn't that a joule?
It's an ampere, isn't it? It's a unit of current. So what we have here is volts over amps. Hey, guess what? Volts over amps, that's ohms, isn't it?
Yep.
So it works. This stuff works. We have, this thing turns out to be ohms. How about that? And we have capacitive reactance. Now let's show you the inductive reactance. That's next. Was there any comment or question on any of that on the capacitive reactance?
So what does the reactance tell us? Like, what does it mean if you have a really big reactance? What does it mean if you have a really small reactance? Can you have a negative reactance?
No, reactance is always positive. And the bigger the reactance, the smaller the current.
Okay.
It's kind of like resistance. See, the bigger the resistance, the smaller the current.
Mm-hmm.
It's kind of like opposition to current, only it's AC, not DC. See, we're talking about AC here. We're talking about alternating current. Okay, now let's do the inductor. We're going to have to say goodbye to all this, but remember that because we're going to need it here in a little bit. Okay, but that wasn't that fun. Yeah. Now we're going to do inductor. We're going to change that. And we're going to make an inductor right here. There we go. Now when this is plus and that's minus, you're going to be trying to send some current through there. And as that current tries to increase, you'll discover that there'll be a voltage across the inductor that will oppose that increase because of Lenz's law that we've studied. It kind of acts like a battery going the other way. It's trying to shove your current the other way. So if you want to know how much that is, it's L di dt. We've studied that. It's a form. Now I know there's a minus sign here. I don't want to confuse anybody. The minus sign refers to Lenz's law, that if you're increasing the current, then the induced voltage will try to send you back the other way. If you're decreasing the current, the induced voltage will try to increase your current going the other way. Whatever's going on, it's going to oppose it. Lenz's law. So now we're going to write our Kirchhoff voltage law, and we're just going to go around the circuit. Okay, well, when you go from here to here, you have V max sine of omega t. And when you go from here to here, you can see you're losing voltage is minus L di dt. And Kirchhoff says that the sum of all the voltage changes around a circuit is 0. Well, there you have it. Now let's do a little algebra here. See if you can get to here with me. Were you able to get to there?
Mhm.
Yeah, no problem. I tell you what, let's do. Let's divide this through by L, divide that through by L, and you can just get rid of that L. Now you have that. And then you have to do a calculus thing to figure out what the current is. Well, the current, you have to, it's like taking the integral. We have the derivative, but what we need is the integral. And when you do that, here's what you get. I'm getting this. We'll make sure that's right. And now to check it, what you'd have to do is you'd have to take the derivative of this and hope that you get that. Well, let's do it. If you take the derivative of this, what's the derivative of the cosine? Anybody know?
Negative sign.
It's a negative sign. So look, there's a negative and you have a negative sign. Hey, that makes a positive. Look, it's positive, isn't it? And it's a sign. So far, so good. And don't forget the, what do they call that? The
Chain rule.
Yeah. When you take this negative sign omega t, you have to multiply by omega. And when you multiply by omega, hey, you know what? I think that omega goes bye-bye.
Yep.
And you know what? You're left with that. That's it. That's it. Okay, now this amount right here, you know what that is? That's your I max. Now we know that the maximum current varies plus and minus. Remember our graph, I erased it, but sometimes it's going one way and sometimes the current's going the other way. But the amount, never mind the minus, the amount is that. So let me write that. The maximum current is V max over omega L. Now I know it's minus when it's going one way and plus going the other, but that's the amount. Now we're going to write the inductive reactance. Here goes. I need a little room. Hey, I got some room. Here's a whole bunch of room right up here. Here we go. Now remember, reactants. The fancy name is reactants. And what it is, it's in ohms, but it's for AC circuits, not DC circuits. And this right here is called inductive reactance. I can't reach that far. Let me write it up here. We're doing inductive reactance. That's the name of it. Inductive reactance, and it's equal to Vmax divided by Imax. That's the definition. Put 3 lines there. There you go. Okay. Let's see what it is. Well, here's Vmax. And Imax, we figured out is here. We just did that. You know what that is? That's Vmax divided by omega L. That's what it says. Hey, those Vmaxes cancel. That omega L goes up in the numerator. We have just found the capacitive reactance. It's omega L. And again, we can look at the units. That would be fun. See, omega is 1 over seconds. It's really radians per second. but radians are dimensionless. And L is in henries, but henries are in ohm seconds, ohms times seconds. So if you take 1/2 times ohm seconds, guess what? You get ohms, don't you? See, capacitive reactance is in ohms. It's equal to omega L. Well, we come up with that now. Any comments or questions so far?
How would we find W, or would we just be given W, or would that just be 60?
Well, let me show you that. Now that's a Greek letter omega.
Mm-hmm.
That little w there is a Greek letter omega. You're familiar with the capital letter omega. That's the symbol we use for ohms. But Greek has capital letters and little letters just like we do. Like for instance, A is the capital letter for alpha, and the little letter in Greek is the little alpha that you all know and love. We could bore you out of your gourd by going through the entire Greek alphabet, but we won't. But you do understand there's big letters and little letters in Greek, just like we have. Now this omega, let me tell you about it. I just need some room here. We can sacrifice some of this. Guys, this is going to be recorded. You can watch this over and over if you want. I'm going to let me go to some of my students. Have any of you ever watched one of the recordings of our class?
Mm-hmm.
Yeah.
I watched one. Yeah, I watched the first one that you put up.
Yeah. Well, each class is on YouTube. And if you want to watch them over and over again, you just have at it. Okay. Now the question was something about omega, and here it is. Omega is 2 pi times the frequency. I think this pen is starting to get weaker here. Now the frequency, that's the 60 hertz. The frequency is 60 hertz, which is a fancy name for, back when I was in school, they didn't call it hertz, they called it cycles per second. And I bet you've heard that before. CPS, cycles per second, but it's the same thing. All it is just one over seconds. A hertz is 1 over seconds. 60 hertz is 60 cycles per second. Now, if you need radians, if you want to know the radians per second, each cycle is 2 pi radians. You guys know that. 2 pi radians in a circle, and you multiply by the frequency, the cycles per second. Look here, 2 pi radians per cycle. You multiply by the cycles per second, and you will get the radians per second. That's it. That's radians per second. It's
Okay.
2 pi times the frequency. Now in
So
Europe,
would it be 120?
it'd be
120 pi.
it'd be 120 pi. Absolutely. Which is, I think 120 pi, if I remember right.
It's about 377. Yeah.
Yeah, it's 377. That's what it is. Check it out. Make sure I'm not lying to you. 120 pi.
Pretty close. 376.99.
Yeah. Okay, I pushed the wrong button. 120 times pi. Yeah, call it 377. That's what we've got. we have 377 radians per second in the United States. Now, in Europe, it is, the frequency is 50 hertz. So if you have like a shaver and you're going to shave or whatever you want to do, plug in some kind of appliance. They don't run on 60 hertz, they run on 50 hertz. So you might need to get a,
But they also run on a different voltage too.
you're
Yeah.
right. You're right.
I think it's 240 or something.
Uh-huh.
Here it's 120.
Yeah, it's bigger than ours. You're absolutely right. Yeah. You might get a converter to do that.
Is there a reason that they're different? Like,
They're stupid. No.
Probably just different grid mechanism. Probably
I'm just kidding. They
probably have a different electric grid mechanism or something.
I
where they just
honestly-
generate their
yeah,
power
I'm just wondering like why they would have a different, like why would they have a different electric grid system? Like what is the reason for
I know
those changes?
in Japan after World War II, they had built their electric grid on 50 hertz, and then when we came in and rebuilt, we did it on 60 hertz. So they actually have stations set up to connect those two grids to convert the 50 to 60, so the grids are compatible.
Wow, I didn't know that. That's interesting. That's very interesting.
probably pretty complicated.
I think I've heard the reason or the answer to your question, but I can't remember it now. I'm sorry. Google it. Just push the Google button and say, well, why does Europe have 50 hertz instead of 60 here in the United States? And Google will tell you. Okay. Well, next, how are we doing? We got time to do some more. And let me put some homework on the board here. I don't want you to turn this in because I'm adding up grades and I want to be finished adding them up. But I've got some homework for you. Let me find it here. Totally organized.
It says that it's purely due to historical reasons.
Is that what it says?
Yeah.
What?
And just to make it consistent over their surrounding area.
Uh-huh. Well, I wonder what Russia has.
I think they have the 50 hertz at 220 volts too.
Okay. All right.
Look, we can take the metric system and they can take the 60 hertz. I feel like that's a fair trade.
That's a thought. It's time for us to switch to metric, don't you think?
It really is.
Way overdue. Okay, now for Monday, let me write this down. I want you to try these two problems. Yeah, try those two problems for Monday.
Will you make those due on Blackboard?
Don't turn them in. Don't turn these in. Just do them, and we'll talk about them. Don't turn them in. Just do them. In fact, let me see what those are. I might go through one of them now. Let's see. I imagine they're both pretty much the same. Okay, we need 15. Yeah, here we go. No, I'll do something different. I know you can do those. I have no doubt. But I'm going to show you one here that's a little different. Okay, now this, I'm going to work a problem here, and it may not make a lot of sense to you yet, but I'm going to try to explain it better on Monday. But there's your homework. Let me write that down so I don't forget it. Totally organized here. This is for Monday. Okay, you write that down here. Let me put it up in the corner up here because I need the room. All right, well, we made a little progress today, and we're going to use it here in this problem. I'm going to erase this now because I need the space. And we're going to do a problem together. And hopefully I can explain it a whole lot better on Monday. This is problem 15.7. And I'm going to draw the circuit now. It says we have a 100-volt AC circuit. We have 100 volts. This is our voltage is 100 volts. And it will be a sine because it's 500 hertz. So this would be 2 pi times 500 t. See, omega is 2 pi f, and if f is 500, then you have 2 pi 500, and so that's just omega t. That's all that is. That's omega t. All right, now here's the circuit. You have an R, which is 500 ohms. And you have a capacitor with 2 microfarads. Two microfarads and an inductor that's 0.2 henries. Okay, now here's our circuit. And what do they want to know? Well, they want to know a lot of stuff. The current. They even wrote this out. They wrote out 1,000 T, 1,000 pi T. You can write it that way. That's better. Let's do it that way. V equals 100 sine of 1,000 pi T. There we have it. All right. Same thing. Okay, well, we're going to find some stuff here. All right. Yeah, all right, here goes. First, we're going to get the inductive reactance. Do you remember the equation for it? It's omega L, isn't it?
Mhm.
So let me get my calculator and we'll do that. And you do it. And see what the omega is 1,000 pi. See it? That's omega. Okay, 1,000 pi 0.2. Did you get 628.3 ohms for your capacitor inductive reactance?
Yes.
Yay! Now we're going to do the capacitive reactance. That needs to be a C. There we go. Now the equation for that is 1 over omega C. We showed you how that came about. We showed you that. Okay. Well, omega is 1,000 pi. But what's C? 2 microfarads. But you have to take the reciprocal. Did you get 159, rounded off to 0.2 ohms. And I'll wait till I hear an uh-huh.
I got that.
Yay, we're doing great. Now we got 500 ohms resistance. We made a lot of progress. And now I need to explain to you about the, somehow I managed to skip this. The voltage in this circuit is a sinusoid, and you all know that what sinusoids do. They do this. Sort of like that. Pretty close. Maybe this goes down a little further. I don't know. Artist rendition here. All right, there you have it. There's your sinusoid of your voltage. Those are your volts. Well, now, what about the current in a inductor? The current in an inductor, I didn't explain that part very good. I should have explained that when I was talking about the inductors. The current in an inductor goes like this. I don't remember if I drew this. Yeah, I think I did because let me make sure that's right. Look in your book. And let's see if I got that right.
Oh, what are we looking for?
I want to see if the current in an inductor, this is the current. Has that kind of a waveform. And
I think for me, it's just the start at 15.3. I think that's what you want.
okay, thank you. Let me shop around here and find 15.3. Here we go. Yeah, there we go. Yeah. Yeah. It's 15.3. Good going. And did I get that right? No, I didn't. No, I did. I'm looking at the wrong page. That's for a capacitor.
Okay.
I was doing the inductor. Now that's on page, yeah. It's on page 675. And do I have that right? For the inductor, I have it wrong. Let me get it right. The current in an inductor, I wish they hadn't changed the colors on me, but the current in an inductor looks like this. This is the current. If you're doing an inductor, and I think I've got that drawn correctly. It's section, I don't know what section it is. In my book, it's page 675. But the way it works is there's a little saying that goes like this: Eli the Iceman Eli the Iceman. What it says that in an inductor, see that L there? In an inductor, the voltage leads the current. This voltage is leading the current. See, time is marching on here. Over here, it's later. And here, it's earlier. Over this way, it's earlier. Can you see that the volts peaks out before the current peaks out? The volts goes down through this axis before the current. The current goes through the axis here later, the time axis. The voltage bottoms out here. The current doesn't bottom out till later. The voltage, E, you can write that E like that if you want. The voltage leads the current in an inductor. And they explain that better in the book than I did. And they even draw the phasor for it. If the voltage leads the inductor, they draw the phasor like this. They have the voltage here, and they have the current here. Here's the current. And these phasors are spinning around, but see, the voltage is always out ahead of the current by 90 degrees. By 90 degrees. The thing is, we have a series circuit, so the current is the same on all the components, but nevertheless, the voltage, the current is going to lead the voltage. The voltage is going to lead the current in the inductor. Now, in a capacitor, it's just the other way around. Need a little room here to operate. Let me come back and try to explain that better to you on Monday, but let me finish this problem. Let me steal 10 minutes from you. We're going to finish this problem. And read this stuff about Eli the Iceman. I don't think they tell you that in the book, Eli the Iceman. But they do draw those circuits. To solve this circuit, what you have to do is you have to make an impedance diagram. We're going to make an impedance diagram, and it's going to look like this. We're going to have 628.3 ohms for the inductive, what do you call that? The inductive reactance. And then we're going to have 159. I think it's smaller than that. It's about a fourth, isn't it? Maybe a little bit smaller than that. Here's your capacitive reactance. It's 159 ohms. And then we have 500 resistance. There's your 500. There's your R. 500 ohms. Now what I'm drawing here is what they call the impedance diagram. And what we're going to do is we're going to notice that these subtract. They're out of phase exactly 180 degrees. So when you subtract that, what you'll get is 628.3 minus 159.2. I'm getting 469.1. When you subtract that, you'll get your XL minus your XC, which is 469.1 ohms. And then you can get your impedance. Your impedance goes right here. And that's these things, these phasors, they're like vectors and they add like vectors. You know how you add vectors. If you have 469 and 500, you've got to do this. You've got to go 469, 500, and you can get your, what they call the impedance. All right, let's do that. 469.1 squared plus 500 squared. I'm getting 685.6 ohms. That is your impedance. The impedance. I'm getting 685.6 ohms. Now we can get the current. I think we'll get the current and then we'll move on and close out this session. Try to tie it together on Monday. But if you need the current's going to be 100 volts. See the 100? It's going to be 100 volts divided by 685.6 ohms. We're going to get our current now. Let me do that. I'm getting 0.146 amperes, 0.146 amperes of current. But see, it's back and forth. It's AC. It's back and forth. We can even get the angle that current's at. We could write the current. The current is 0.146 amps sine of, what is it, 2000 pi? Is that what it is? 2000 pi t minus.
Should be 1000 pi, right?
Another thank you point goes right here. You're absolutely right. It's 1000 pi.
Where are you getting? Oh, yeah, sorry. Yeah, I understand now.
Minus this angle. See this angle right here? It's got a name. It's called a phase angle. We could get that phase angle. That's not a problem. Let me get it. Let's see. There's several ways to get it. You could go 500 over 685.6 and take the arc cosine. It's 43.2 degrees. This angle here is 43.2 degrees. We think this is the current. It's a sinusoidal current, and we have the angular velocity. We even have the phase angle. Now let's look and see if we got the right answer. I was trying to do 1527, And I'm going to look that up and see how I did here. 15. See if I can find 1527. I don't know. 1527. I'm curious to see if I got that right. 1527. Okay. 15. Did I just do 1527? That's what I thought I did.
Yes.
I don't see the answer to it. Oh, that's the wrong chapter. Just a minute. Let me find the right chapter. That might help. 1527. They said, well, here's the answers. They said 690 ohms. Oh, they're a little bit sloppy. You know what? The book says 690. That's supposed to be an ohm right there. The book says 690 ohms. Man, that's kind of sloppy. Now the book says 0.15 amps. Hey, they're kind of sloppy, aren't they? The book says 0.15 amps. That's pretty close to what we got. We got 0.146. I think they rounded off. And then here's their here. Let me write their answer here. They said I. This is the answer book. They said I is 0.15 amps. Sine 1000 pi t, 1000 pi t, minus 0.753. Well, see, they put it in radians. I bet you 0.753 is 43.2 degrees. Can you guys read all that?
Mostly, yeah.
You got better eyes than I have. Let's convert 0.753 to degrees. 0.753 radians. You multiply by 180 and you divide by pi. Boy, Jove, I'm getting 43 degrees, 43.14 something degrees. Hey, we got the answer. They did. I think they had some other answers, but it gives you a little taste of where we're headed here with AC circuits. You do those for Monday. We'll have some more fun on Monday. Any last words or comments before we adjourn?
Could you go over really quick the not doing them, but just explaining which homeworks that you've recently given us were we weren't supposed to turn in and which ones we were supposed to turn in? Because I just have a stack of stuff and I'm not sure which ones I'm supposed to turn in and which ones I'm not supposed to turn in.
Yeah. Now who is this speaking?
Logan.
Okay, Logan. I'm looking at Logan. What's the last name?
Jones. Logan.
You are missing 2 homework assignments, and you got your
Okay.
pencil?
Yep.
1127 and 1141.
Yep.
Now, I don't have any grade for you, Logan, on 1127 and 1141.
Mm-hmm.
So
And what's the other one?
the other one is 1223 and 1225.
Okay.
I've got a lot of grades for a lot of other people here, but on those 2, I don't have yours.
Okay. All right. I will turn those in. Yeah, I would just got confused about which ones I was supposed to turn in, and I didn't write that down. So, all right, I'll get those to you.
Turn it in. I'll try to be kind. Anybody else?
Thank you.
Am I missing anything?
Well, let me look at you. Not on this page. You got some good grades there. Not looking good, Kristen.
Okay.
Nick.
Scott Hemphill.
Okay. Scott. I'm looking at Scott here. Okay, now, Scott, I got some empty spaces here. It's a little bit like West Texas. There's some wide open spaces here, Scott. There's
Okay.
11, 11, 19, 21, and 25. Turn that in. Maybe I'll be generous. We'll see.
Okay. I think I've been emailing the assignments and I did the one on Blackboard. I thought the only thing I missed was the lab.
Yeah. Now I don't have that lab either. That current loop lab. Do that and turn it in. We'll give you some points.
Okay.
And the one other thing, Scott, 1223 and 1225.
Okay. I think I've done all those. Do you want me to email them to you again?
Can you do it and submit it on Blackboard?
I don't know if I can.
We can't unless you give us a thing to turn it into. The only way that we can give it to you, unless you put a submission thing on Blackboard, is for us to email it to you.
You're absolutely right. And I don't remember if I had those on Blackboard.
You did not.
Yeah, you did.
You're going to have to do it the old-fashioned way, Scott. Take a picture, send it to me on the email.
Okay. I
But
can do that.
we'll put something in the book here. We don't want to have empty spaces there.
Yeah.
Next,
Chris, spellings.
Chris. The only thing you're missing is that current loop lab.
I did that. And you gave me a grade for it.
What'd I give you, Chris?
A 10.
You know what? I think I owe some other people. The people that got 8s, I need to up them to 9s.
I've got it right here on my email.
Well, I believe you. Because Mohammed informed me that I had a wrong answer on the very tail end. I didn't double the answer. So if you got a 9, I'm going to up that to a 10. If you got an 8, I'm going to up it to a 9. I made a mistake on that last answer. I haven't done that, but I will. Next.
Yeah, I think he.
There he goes.
Oh,
Oh, there you
you're back. Okay, we couldn't hear you for a little while. You cut out.
Oh, I cut out.
Yeah, you cut out for about a minute, but you're back.
Well, we were going over any grades that people missed. Anybody else want to
Yeah, we
ask?
were out just for a couple seconds.
Anybody else want to ask about a grade here?
Mohammed Khan.
Now, tell me who this is, please.
Mohammed Khan.
Oh, yeah. Okay, I see you here. Mohammed, the only thing you're missing is that virtual current loop lab.
I did that and you give me 8 and you're supposed to do it in 9.
Okay. I'll fix that, Mohammed.
Okay,
I'll fix that. Thank you.
you're welcome.
Next. Anybody else?
Yeah, you might as well check me. Levi?
Now, who am I talking to, please?
Levi Johnson.
Oh, yeah, Levi. Okay, here, Levi. You're missing 1369, Levi.
Well, I did that. Do you want me to resend it to you?
Did I? Now that's on Blackboard.
Maybe I didn't submit it. I'll submit it. I did it.
Well, you should be able to submit that on Blackboard.
Yeah, I will. I did it. I don't know why I didn't submit it. I thought I did.
Well, one of us made a mistake. Just do it again and we'll fix it, okay? We'll fix it.
Thank you. Sounds
Yeah.
good.
Thank you. Anybody else?
See you tomorrow, Professor Griffin.
Hey, I'll see you tomorrow at 9:30.
Yep. Have a
Mr.
good
Griffin,
have a good evening.
I did submit it. You gave me a 4 on it.
Holy cow. Was that Levi?
Yes.
Levi, we got you covered.
Thank you.
Thank you. Okay, guys. Hasta luego.
See ya.
Alrighty.
Bye.
Later.
Yeah.
Bye-bye.
Professor. Can you hear me?
Yeah, go ahead.
Ross, could I just check, make sure there's nothing out? I do,
Yeah, Ross.
I know there's several classes, but it's a little more difficult.
Yeah. Okay, I'm looking at Ross now. Now tell me the last name, Ross.
Latcham.
Oh, yeah. the only thing you're missing, Ross, is that Orsted lab that we did a long time ago. The,
I
Or-
got,
the Orsted lab, and it has to be submitted on my mind just went blank on the email, Ross.
1 second, sir. I can pull it right up and I can resubmit it to you with your words so it'll pop up
Good.
towards
do
the top
that.
on your email if
And
you want.
Professor
Yeah.
Jeff is asking if you'd check his as well.
Yeah.
Okay, I'm going to look at Jeff now. Hang on.
I just don't know what you gave me. I can't remember if it was an 8 or a 9, but I know you did give me a grade for it.
Okay. Jeff,
Let's
the
find.
only thing that Jeff is missing is 1223 and 1225. And I don't remember if that was on Blackboard or email.
Mohammed Savanti.
Yeah, okay, Mohammed, just a minute. Mohammed, the only thing you're missing is that virtual current loop lab.
I did submit that.
I didn't get it. I don't have any mark for you, Mohammed. Did you submit it on Blackboard?
Yes, I did.
Well, what did I give you? Do you remember?
Hey, 10.
Say that again. I didn't hear you.
For which lab?
For the current loop lab.
I think it gave me a grade for that. I'm just checking right now.
Okay.
Professor,
Yes.
you gave me a 10 on the Orsted lab.
Oh, okay. Now who was that?
That was Ross Latcham. Or this is.
Okay, Ross. Just a minute.
Do you need me to send your email back to you for proof?
No, you don't have to do that, Ross. If I can just find, here you are.
So, but for physics, you don't have any other gaps?
Nope, you're filled in.
Awesome, sir. Thank you.
You are so welcome. And
Professor Jeff said that he did that. He's going to send your email back to you.
good. Do that. That'd be wonderful.
Was that on an email or for that lab?
I think it was on Blackboard, but I could be wrong, guys. I could be wrong. Well, I'm going to sign off, and you still have more questions, ask me on Monday. And
Appreciate your time, sir.
thank you, everyone. See you guys later.
Bye.